Here I have a wheel, actually just a piece of styrofoam with some bolts in it, and I can have that mounted on an axis so I can rotate it. Now, imagine we have a coordinate system centered right here, and we've got a vector r of t goes from here out to this white push pin. If I rotate this thing, my r of t vector continually changes, and the tip of that r of t vector describes a circular motion. It goes through a circular motion that can be described by an appropriate function r of t, where t's understood to be clock time. Now, if I put another object here so that it can rotate about an axis, it's not very good, not very free in its rotation, has some friction. I'm going to call this vector now r1 of t, and it goes out to the point directly below here, and I'm going to call this vector, let's label it on this side, r2 of t. It's not written very clearly, but you can understand that here we have a vector r1 and here we have a vector r2. Now, if this bigger disk is rotating, then of course the r2 disk or the r2 vector moves along with it. If this is also rotating, so that we have two rotations, we have the larger disk rotating and the smaller arm rotating at a different rate, then the position of this push pin would be described by a vector that goes from the axis out to the blue push pin. And that vector would be r1 of t plus r2 of t. Now, if r2 of t has an motion independent of r1 of t, then we can see that we have a model in the function r1 of t plus r2 of t that gives us the motion of this blue push pin. And we can depict that situation. We have a, well, we could depict it if we had clear focus. Let's see if we can achieve that. Come on, come on. Let's try again. Here we go. Okay, now maybe we're back on the paper if I keep my hands there. Okay, if we have a coordinate system, then the path of the r1 vector is going to be a circle. The path of the r2 vector is going to be originate from the end of the r1 vector, and wherever that r2 vector is at clock time t, we'll have the vector r2 of t. And I've labeled these somewhat clumsily. But we have now the vector r of t equals r1 of t plus r2 of t. And if we know r1 and r2 both as functions of t, we're going to be able to trace this point out. Now, the path might look something like this. Let's say at t equals 0. The axis of the rotating piece of foam on the circle is at this point, and the beam is oriented in such a way that the vector is here, so that that would correspond to this orientation where the R1 vector is added to the R2 vector, giving us a point here. Now if the larger disk rotates slowly, what's going to happen? Well, the R1 point might come out to here, and the R2 vector might have already rotated to here. So now we'll be at this point. Now if we rotate a little further, let's say we rotate up to here, and the R2 vector has come all the way back in this direction. Now this figure isn't working out very well, but the point might be here. And the path might look something like this. And that would be the path described by the vector function R1 of t plus R2 of t We'll look at how we might do this mathematically in the next clip.